Welcome to the Global Composite Webinar Series. My name is Wenbin Yu. I'm the Director of the Composite Design Manufacturing Hub. I'm delighted to have all of you join us today for this exciting webinar. This webinar series examines the history, recent capabilities, and the future of composites. Our goal is to share the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. Our center is located in the Indiana Manufacturing Institute. We welcome all of you who visit us and explore the cutting-edge facilities and resources available at our center. At the CDM Hub, our mission is to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. Our ultimate vision is for CDM Hub to become the premier resource for composite design and manufacturing. To achieve this mission, we have developed a powerful website called cdmhub.org, which serves as the platform for the composite community to collaborate and innovate together. We invite you to join cdmhub.org and take advantage of all the knowledge and resources available on the website. This webinar series is just one of the initiatives that the CDM Hub has launched to serve our community. This webinar series is made possible by the generous support of our sponsors, Dassault Systems, Cytec Solvay, and AnaSuite. We extend our heartfelt gratitude to our sponsors and acknowledge their commitment to advancing the field of composites. We also welcome other organizations to join us in supporting the global composites community. Together, we can create a bright future for our field. This webinar will be recorded and made available on cdmhub.org. We will email you once the recorded video is available online. The presentation will be about 45 minutes, followed by a 10-minute Q&A section. All attendees are muted. We ask you submit your questions through the Q&A box. To ensure that the speaker has adequate time to effectively answer your questions, these questions may be summarized or rephrased. But please rest assured that all questions will be forwarded to the speaker for answers at their discretion. Now, I would like to invite Professor Dianren Zhang to introduce our distinguished speaker for today's webinar.
Thank you, and welcome everyone. I'm honored to introduce today's webinar speaker, Dr. Henning. Dr. Henning is the director of the Fraunhofer Institute for Chemical Technology and has been a fellow of the Society for the Advancement of Materials and Process Engineering, SAMPE, since 2020, and a fellow of the Society of Plastics Engineers since 2013, and is acting president of SAMPE Germany. Since 2016, he has been the managing director for the Fraunhofer Project Center for Composites Manufacturing in Ulsan, Korea, and since 2011, the Fraunhofer Project Center for Research in London, Ontario, Canada. In 2017, he received the Minister of Trade, Industry and Energy Award by MOTI, Korea, for international collaboration on leading-edge technology development. Dr. Henning studied mechanical engineering and holds a PhD degree in composites engineering from University of Stuttgart in Germany in 2001. He published numerous articles in refereed journals and owns patents in the field of polymer manufacturing. In 2008, Dr. Henning was appointed professor for lightweight technology at the Karlsruhe Institute of Technology in Germany. Since 2010, Dr. Henning has been an adjunct research professor in the Department of Mechanical and Materials Engineering at the University of Western Ontario in Canada. Dr. Henning has been awarded multiple times for his achievements and introduced materials and technologies in industrial applications. He has more than 25 years of experience in polymer engineering with a special focus on composites processing. Now I will give it to Dr. Frank Henning.
Yes, ladies and gentlemen, it's a pleasure to speak here at the Global Composite Experts webinar. And I want to contribute with a presentation which is describing our M of the Power 3 approach, a sustainable approach to vehicle lightweighting with composites, a holistic approach where we employ methods, materials, and manufacturing in a holistic approach in order to get to an efficient lightweighting solution. All the work that I will present is presented with my colleagues and a lot of PhD students that comprehensively are doing ongoing research in that field of composites. And with this presentation and the introduction I want to start with, you see here the agenda. I want to introduce our location, Karlsruhe, with the KIT and the Fraunhofer ICT, a little bit with the research that we are accomplishing there by going through some examples that we developed in the past using the M to the power 3 approach, and then going a little bit more in depth in a technical approach on wet compression molding, how we employ this M to the power 3 approach, and then I will move on to some sustainable and circularity aspects that our industry will for sure face a little bit more intensively in future, ending my contribution with the trends and outlook. First of all, I mean, Fraunhofer is one of Europe's largest research organization with more than 30,000 people working for the institute, spread over 76 institutes all over Germany, co-located with universities, and we as directors of these institutes are also at the same time professors at local universities, being involved in teaching as well, and in some basic research, but our focus here at Fraunhofer is clearly the applied research. So 1/3 of our total budget is pure industrial research, and another third is borne by a funding body, usually EU, federal government or state government, where we collaborate with industry intensively on competitive questions and proposals that we have to hand in and compete for. And 1/3 is basic research that is being relying on funding from our local governments. Fraunhofer, in the whole group of the institutes, are following certain impact goals that are determined together with our government, which are shown on that slide. So the impact goals that has been identified are the completed energy transition, the fully circular economy, the digitalized value chain, security, and the resilient society, and as well as affordable healthcare. Those fields, those impact goals are fueled by our overall research fields that we are working for: artificial intelligence, digital healthcare, next generation computing, quantum technologies, resource efficient climate technologies, and hydrogen technologies, as well as bioeconomy. And all these, let's say, more green dyed fields that you see here is where ICT is contributing to amongst the other Fraunhofer institutes which are active in this field. So a lot of these individual research that we are conducting are also through the individual institutes, are also together with other Fraunhofer institutes and universities. As I said, focused on industry, we are target lead markets, which also are identified together with our government. Those are plant, mechanical, and vehicle engineering, healthcare sectors, digital economy, construction industry, mobility sector, chemical industry, energy sector, food industry, and aerospace industry. And as well, what you can see here, the dyed, the bluish or greenish dyed fields are the lead markets where we either contribute or we have the lead. So Fraunhofer ICT is leading the lead market, Fraunhofer Alliance for Chemical Industry. Now, when we look into our institute, we have 4 core competences we look at. One is chemical processes, non-fossil chemistry, electrochemistry, chemistry with hazard potential, etc. Polymer engineering. And within the group of polymer engineering, there's also the group for lightweight design and composite engineering. Then we have the energy and drivetrain system. And then we have a defense sector, which is also in explosives, safety and security. It also has to do a lot with filled and reinforced polymers, just with an energetic background and not a structural background. So these 4 core competences are being served with about 550 people, which are located at our institute. And you see it's a pretty interdisciplinary approach where a lot of synergies can be derived from. And a few I want to introduce in the beginning so that you can get a good imagination who we are and what we are doing. Now, polymer engineering, I just picked 2 departments out of that family of departments that are fueling these core competencies, which are of relevance for today's presentation. One is the Department of Polymer Engineering, where we look into material development and compounding, not from the perspective of synthesis, but from the perspective of modification, physical modification, filling, reinforcing, foaming technologies, a big subject at our institute, additive manufacturing, injection molding and compression molding, structural lightweighting, where I will talk a little bit more in depth today about wet compression molding, microwave and plasma technology, and obviously we have to get our material data cards filled. We do a lot of material characterization, and also when we do part development, failure analysis, etc. A topic which I want to mention because we use it more and more in our projects is environmental aspects. Evaluation on sustainability and circularity assessment, but also recycling technologies, bio-based materials, bioeconomy, and subjects like environmental simulation and product qualification for our industrial partners once we develop prototypes that we can undergo artificial aging process and exposure process to environmental threats to qualify the product. Our institute, as I said, is one out of the 76 in Germany, and we are truly international. As mentioned in the introduction, I had the pleasure, together with my colleague Andy Rymack and Youngbin Park, Andy Rymack from Western Ontario in Canada, and Youngbin Park from UNIST in Ulsan City, Korea, to collaborate in the field of composites with our competences and our main location here in Germany, having these 2, I would say, innovation platforms that has been established. Canada is the oldest one with more than 10 years active now in the field of composite research, and UNIST more than 6 years now being active in the field of composite manufacturing. And a pretty new one that we opened together with our partners in the Czech Republic with a focus on applied artificial intelligence for materials and manufacturing with the University of Ostrava in the Czech Republic. I mean, lightweighting and composites are already a contribution to sustainability. But especially at our institute, you see it in my background, you see the windmill sticking out here. I want to introduce a few highlights that we looked at. Our mission is research for a better future. You find some selected topics related to sustainability already on this slide. Sustainable energy solution, lightweight technology, that's what we address today. Technologies for recycling and circular economies. Powertrain technologies for future sustainable mobility applications. And by developing this, we also want to develop them in a sustainable way. So a quick introduction to this exception that we have here, having our own power plant. We are running not just a power plant, we have also energy storage devices, as you can see here. And energy storage devices are becoming increasingly important as a result of the German energy transition. They can compensate for natural fluctuations in solar and wind energy and thus convert the renewable energy source into a predictable generating station with uninterrupted supply. They can also make a decisive contribution to grid stability and frequency control and reduce the need to extend the grid. In the framework of the projects that we are running, one is the Redox Wind project. A large-scale redox flow battery storage device has been developed, as you can see here on the right side of that slide, and connected directly to the intermediate DC circuit of that wind turbine here. And this unit, consisting of a generator and a battery storage device, has been constructed as a pilot unit at our institute in Finstal. We add this year 800 kilowatt of solar energy so that we are getting more and more independent of external energy supply, and basically are routing into a CO2 neutral energy support. And by the way, quite a bit of composites are already used in the wind turbine, and also, as you can see, in the battery storages. From there, going to efficient, weight-efficient powertrain applications for sustainable mobility. 3 examples that I want to show to you based on projects that has been done in the past. One is a lightweight battery module, where the conception, the development of a lightweight traction battery system, which using innovative design methods and processes serves as a prototype for the e-mobility of the future, with a direct tap cooling of the pouch battery cells, a high-performance thermal management system designed to allow for high charging and discharging rates without derating, or a lightweight traction motor. That was a really nice project. It's a motor which is directly cooled by a composite housing. It guides the water directly to the copper heat emitters, if you like. So the selected cooling concept significantly increased the continuous power density of the motor compared to the state of the art. So it's not just lightweighting, it's also functional integration or boosting of the power generated. Then even for combustion engine, here you see the aim of a funded project called LIMOD, where we focus with the development of a future internal combustion engine with a significantly reduced mass, improved operation efficiency, thermal management, and reduced noise levels. That's obtained by combining additive manufacturing methods and large-size, lightweight, structural, and functional integrated composite side covers. The engine concept is optimized for the combustion of non-fossil fuels, such as green hydrogen. Now coming to our main mission, lightweighting, reducing weight in a holistic way. So we spent quite a bit of thought on what is the definition of lightweighting. And as you can see, it's complex because it's not 2 words, it's quite a sentence. And it shows already the aspects that have to be considered if one wants to be successful. So lightweighting design is a holistic implementation of a development strategy aiming at realizing the required function under given technical, economical, ecological, and social constraints through a system of minimum mass. We often, as engineers, we dive right into the technological challenge, and that's our mission as scientists. And then the industry knocks on our shoulder and says, well, there are economic boundary conditions, and that's the range is being small, reduced significantly. And then now we have societal, political, mainly driven by ecological and also social constraints that are influencing the tool set in the playground. We can develop our solution. Therefore, we do need interdisciplinary approaches if we want to succeed. We have to develop a kind of a system thinking and understanding before we select materials and processes. We have to understand the materials and processes that we are selecting. We have to learn how to predict them, and we have to learn how to manufacture and predict manufacturing in order to use the materials in an efficient way. Not just because of weight reduction, but because also of cost reduction and ecological impact reduction. And that embedded in a social and environmental boundary condition. That's our fertile ground where we have our m to the power of 3 approach being embedded on. The lightweight design success is always through the material, the manufacturing process, but also the joining innovations, because every system has different boundary conditions, as I said, and a lightweighting solution which is economically successful looks different in aerospace than in automotive. And we also have to think, how can we work collaboratively with other materials in order to get to a system solution, which can end up in a hybrid solution as well. When we look into different markets, we can name a huge success story pointing in the aviation sector. And when we look here, what you see here is 100 years of aviation with different airplanes, very familiar, and the weight, the takeoff weight, and the reduction that had been basically achieved over the past 100 years. And how, by the selection of the most wonderful materials you can imagine, most expensive as well, but there's a business case for it which is different than that from automotive. So we cannot copy these solutions to automotive and think that we can be successful as well. We have to have this holistic understanding, which I want to talk about today a bit more in detail. When we change the scope and look into automotive, then vehicle design is subject to a different field of tension. As I said, business case is different. The vehicle is most time in the parking lot, whereas the airplane is most time in the air, earning money with the weight saving, right? We have high volume, we have high cost pressure, we have increased safety and efficiency requirements, increasing quality and functional requirements. We have more individualization boundary conditions, and we have to switch over to a sustainable mobility. So we are in a transition right now. And all of a sudden, with new drivetrains, new vehicle concepts, new material can come into play in areas where they couldn't, because we don't have a combustion engine anymore. But we have a very heavy battery to carry with. So when we see from the regular combustion, that's the curve in automotive. So it's not declining at all. It's still inclining. We could flatten the incline. And we could be more efficient by innovative material and material combinations, but we added more and more safety features, comfort, and functions to the vehicle, and all of a sudden, the big jump with the batteries that we have to accommodate. So yes, lightweighting plays a continuous role in automotive, in order to be efficient, because the volume of automotive is much higher than those of airplanes. Now, since we can't go with the same approach, we have to think about so many boundary conditions in terms of platform strategies, large volume production, etc. In most of the cases, it's a smart solution to come up with a multi-material design. So how do I bring the right material in the right place, so to say? In theory, wonderful. In reality, challenging, because we have higher complexity, we have the delta alpha challenge, what we call it, like different thermal expansion of the different material. We have to join them. We have to maintain that marriage until the end of the product life. We have to ensure repair, maintenance, etc. And we have to make sure that we separate those material design after these different materials after lifetime, in order to be recycled appropriately. But on the other side, we have a couple of advantages we want to take advantage of. Like you see here, I don't want to read those individually to you, but I think to find the sweet spot is always a challenge, requires the toolkit I'm talking about, and requires a common interdisciplinary approach. The material class with the highest potential on lightweighting is, and what we had prior to this talk today in our conversation, is fiber composites, because they are still the youngest group, and they have an additional benefit, the anisotropy, because they can also be designed on the material level already, and not just in the part design. When we look into the efficiency of lightweighting, and that's a vehicle life cycle, you see that in the vehicle life cycle, 85% of the CO2 emissions are being generated during the life cycle. So yes, it's worth spending a lot of effort on lightweighting and employing new materials. Just 0.1 is in recycling. But in order to improve this footprint, ecological footprint, we have to take that out of the equation and then just look at material production, raw material supply, vehicle production, recycling. How can we decrease the gap when we do a life cycle analysis versus a circularity analysis, and see what do we gain back after life cycle and what gap do we is still left, and how can we minimize that by employing appropriate materials, and also materials maybe in future that are more based on natural sources. Now, quickly, how do we distinguish the world in composites at our place? We talk about continuous and discontinuous fibers. That's our abbreviation here, co-FRP and deco-FRP. And then we have the nice combination of both, the co-FRP. So that's a co-molding of discontinuous fiber reinforced polymers to continuous. I apologize the complexity of the slide, but that summarizes basically our world of thinking here. What you see here is the continuous fibers. Here's the discontinuous fibers. These are structural applications. These are more functional lightweighting, totally different performance here, and also completely different process technologies because it's a flowable material. The completely different material behavior can be processed differently in much larger numbers, much more complex compared to the continuous fiber reinforced materials. So it obviously makes sense to think also about the combination of both in an efficient way, where we have the best of both worlds somehow combine structural performance and functional integration. The greenish fields are distinguished between thermoplastics and thermostats, and what you see here, and that's a summary basically of what we offer here in our area, is medium to large scale automated technologies for composite manufacturing with a focus on medium to large scale, as I mentioned. So that's our technology portfolio. Talking about the approach now. The idea behind this approach was an efficient and sustainable lightweight solution that is based on a holistic understanding. So how does that look like in a simple two-dimensional graph? We have the societal and ecological boundary conditions in which we are having our design space and room for finding our lightweight solution. And then we have the economic boundary condition. How many parts a year? What is the maximum cycle time we can derive for? How much automated do I need to process my part? And obviously in automotive, we cannot do quality assurance part by part. We have to quality assure the process. All of a sudden, the process gets expensive because it's automated. But it's negligible in terms of the number of parts you're being produced. You will produce with this technology compared to aerospace, where you have to consider manufacturing technology costs much more intensively because it can be amortized the same way. So you see, I'm just highlighting some of these constraints that we have to think about before we start selecting an appropriate material for an appropriate market and an appropriate application. And then we look into how many parts, what are the suitable manufacturing technologies, what materials can come into play. Also here in automotive, more the commodity materials, in aerospace, more the high performance materials. And how can we produce efficiently, and how can we secure that with the understanding of the materials, simulation methods, predicting the manufacturability and the manufacturing influence on the material, whether that material is suitable in that shape to fulfill that function. And then we get to a lightweight solution which is economically, ecologically, and technically, obviously, feasible and socially accepted. We can do that as a one institute. We have our partners. So we formed a house of competence in Karlsruhe, where the superset goal of the interdisciplinary lightweight solution is being supported by the development of methods, development of virtual process chains for different type of materials, for different process technologies, process simulation, structural simulation, and then also optimization of products and design and artificial intelligence supported manufacturing. Then we have the materials, where we need to fill our material data cards, where we do the characterization, the understanding of the morphologies influenced by the processing as well. and translate that into suitable manufacturing technologies, or consider that at least when we select suitable processing technologies. And then basically through our partners, we do projects at the different innovation platforms or with our spin-off companies that also are part of the transfer. Talking about the M⁻³ approach, methods, material, and manufacturing, I brought an example of a past project that we conducted a couple of years ago already, the so-called SMILE project, where the major focus is the development of concepts and design for an innovative mixed material body for an electric vehicle that was without steel, so that we don't have electrophoretic painting, which is an advantage because we don't have the painting process and therefore don't have to use that high performance resins that we have to use when we have to undergo this. The development of a virtual process chain for component and total cost optimization, the validation of the structural integrity and the crash requirements at component level. We are focusing on two parts. One is the floor thermoset with ultra resin transfer molding. It's a pressure controlled process, and the other one is thermoplastic tapes overmolded by LFT. That's a rear body structure that's more the crash element, the energy uptaking, and the passenger cell more stiff. Stiffness optimized is a thermoset. So the advantages through a holistic approach and a continuous CAE chain is to consider manufacturing effects and their influence on structural behavior, to verify the manufacturability, and to have iterative optimization at the simulation level without having a lot of testing and molds development, because these kind of molds are expensive. So we want to have a virtual design and optimization of a product and a process up front, which accelerates the part development and results in reduced design loops. Now, having just a focus please on the second part, that's the mold filling displayed in this video, what you see here. In order to get there, we have to understand all these different steps, the forming prediction, the local fiber content, and also fiber orientation, permeability changes, and then the resin. The resin that's tested here. That's why I say material, a method, and production. We need to validate that so that we can use that for further part development afterwards. You see here a couple of publications below. That is a lot of this work is coordinated, done by my colleague Professor Kerger, who together with me is running the research institute at FAST for lightweighting. And we are also working with our material characterization folks. You see this plate rheometer is a special development because these highly reactive resins has to be mixed and injected immediately, because when you do it in a conventional way, it's already cured before you start measuring. So we have to adapt methods to get real data for what's happening in the process during the manufacturing, which is a couple of seconds only. And then when we have the mold filling, which is pretty accurately, we have different wall thickness, we have sandwich structures in between. Then we do the cure simulation, and from the curing we derive stresses and also warpage that help us to control part tolerances. Now the back structure you see here is a tape placement, or Ganner sheet if you like, thermoplastic, hot, then molded, as you can see here, with a segmented mold. So it's like ironing a textile from the top to the bottom, from the inside to the outside, in order to avoid wrinkles. That has been determined. So by the simulation, we can predict which area has to be draped first and which last, in order to avoid wrinkling and get an appropriate wrinkle-free preform. And then this is, together with the aluminum longitudinal carriers, crash carriers, is being inserted in the mold, and then it's overmolded by a discontinuous fiber reinforced thermoplastic, which already also joins the material at the same time to this part. Two examples where this holistic M⁻³ approach has been applied, and I want to go a little bit more into the detail with wet compression molding. And I would like to illuminate this M to the power of 3 approach by using a research collaboration between the KIT in Karlsruhe and the University of Stuttgart, the Institute for Airplane Design, into the enabling of the wet compression molding technology. You see here the video. It's a transparent mold so that we can see this greenish resin on top of the fabric that is being spreaded, impregnating and forming at the same time. We want to compare two routes. The green one is being investigated by our institute, the blue one by the Institute of Airplane Design. They're using preforms. We want to do that in a direct process, so while forming, we are impregnating to save one step and to see whether we get to a suitable robust process by investigating this. Here you see some parts on the left-hand side of parts that are being in industrial application, the Beam W7 series right now. Let me introduce the process steps for now. So there are 5 process steps. One is the cutting and stacking of the individual textile layers. Then we have the resin application on the top. Then we transfer the textile layer stack with the resin into the mold. We have a kind of a viscous draping. We have a curing. We have a demolding. Okay, it's working. So the main physical mechanisms during forming are, as you can see, viscous draping, infiltration, fluid structure interaction, and curing. And that's not happening all at the same time. The interaction is different during the closing of the mold. So there are process phases, which are highlighted here on the far right. First part is dominated by drape mechanism, membrane, bending, contact, compaction. Then towards the end, the forming process, the relevant fluid pressure occurs locally. This is critical for fluid structure interaction, so we can have a fiber displacement by having this resin being squeezed out. And the last 5% approximately are characterized by compaction and high fluid pressure. Forming is largely completed at that point. How can we use this M to the power of 3 approach to systematically investigate such a complex interaction? First, we must characterize the material on a coupon level to understand and parameterize the mechanisms. Second, we need to derive simulation approaches describing this behavior and feed them with the characterized parameters. Third, derived from the material behavior, we can develop the process and understand interactions and limitations, leading to a geometry which is moldable without defects. So these 3 areas we'll go through. First, the materials. What you can see here. Step 1 of this approach, material characterization. So material behavior of dry and infiltrated reinforcement is crucial to predict shaping in the mold. Relevant deformation mechanisms, membrane, shear, bending, contact and compaction behavior. Contact here is omitted because of timing and space. Examples are here show the membrane behavior. So infiltration determines the thrust behavior influenced by the friction between and within the contact points of a fabric, as illustrated here on the left side. The consequences of infiltrations are that friction changes, both at the crossing point and within the rowings. In addition, the compaction behavior is changed, and that influences the locking angle. The new test rig is shown here. So you see here the fluid basin. So that's a test rig that has been developed. We call it the IBET, the Infiltrated Bias Extension Test, where the shear deformation was measured in a fluid basin at complete wetting. At that case, the camera from the top is measuring the current shear angle in the center of the specimen. Obviously, we have the 3 zones: no shear, half shear, full shear in the center of this bias extension test. And finally, the drape behavior, and that's what you can see here nicely, can be improved as well as be deteriorated compared to a dry fabric, which is very important for the process and the mold design. So it has to do obviously a lot with the viscosity and the reactivity of the resin, which is the viscosity over time. Another important material aspect is interaction between permeability and compaction. Permeability is determined via a one-dimensional flow according to Darcy's law. A gap is approached, we have a constant volume flow which is set, and then we measure the pressure difference stationary. In plane is self-measured, even for sheared samples we need to measure that and determine, and through thickness, that's something we did externally at Fraunhofer colleagues in Augsburg. The process simulation uses a fiber parallel reference system to describe the anisotropic material behavior, Lagrangian description method, and the description of the permeability taking into account the current fiber orientation makes it possible to intrinsically capture the influence of shear. Fluid mechanics, here a complex conversion must always be made to account for shear and fiber orientation due to the space fixed reference frame coordinate system. This is a great advantage compared to an Eulerian description. Fluid mechanics here, due to the spatial reference system, a complex conversion must always be made to account for shear and for fiber orientation. All right, compaction, another material characterization. We observe a nonlinear tri-material behavior, and with additional infiltration, we see that it leads to an increased reaction force, since the incompressible fluid now must be squeezed out through the material, and therefore we have a changing porosity, a changing permeability at the same time, and we have to map this interaction between deformation and permeability, which we consider crucial for robust process simulation, and obviously if you want to predict press forces or compression forces. So we see quite a bit of dependency, fiber volume content over the reaction force depending on dry or pre-impregnated textiles. Now here the process is being illustrated. That's the second step, now the method development, based on this material behavior that we just investigated. So we developed a drape test rig for the investigation of material behavior for an in-depth process understanding and for validation of models. Then we looked into the development of a corresponding simulation model for a transparent double dome test rig. The modeling of the tool areas is relevant for forming and modeling the material behavior. The discretization of the complex problems takes place by means of finite elements with special properties, followed by the solution of balance and constitutive equations in the discrete elements. In the right picture, the development and coupling of special finite elements, drape and fluid submodel, to represent the material behavior previously observed in the experiment. Solutions of the submodels is coupled and simultaneously, thus a direct interaction is captured. This method considers material behavior under process boundary conditions with single independent layers, since slippage during forming has been considered as important. Well, now the next step in the method development is to validate methods and to use for design of the part. Yeah, here you see shear angle depending on the geometry, fiber volume content depending on the geometry, and fluid volume per element. The demonstration validation has been performed with a transparent double dome mold. So that's a bottom and top simulation view and the reality of the resin. And you see it's pretty nicely described here. The only thing that we couldn't consider with that model is the free surface flow. That is not explicitly considered here. Click. Oh, it's gone. Yeah. Use of the methods that we developed here for the design and the structural prediction of the demonstrator geometry is the next step. So we want to investigate and optimize the geometric features. We want to investigate whether these geometries are manufacturable or not, and optimize them, determine maximum acceptable geometry, fiber orientations, and load path. So the virtual process and mold design that is basically going hand in hand together is securing the tool design in the end and the prediction of the critical points. We can also derive from there the global blank holder, or whether we can use a monolithic stamp, or we have to derive from it a multi-core stamp. Finally, the third step of the M to the power of 3 approach is to utilize the previous findings to design an efficient process and understanding and predict the bed compression molding technology, shown on a complex demonstrator. And that is the sled. What you can see here is a carbon sled with this multiple layers of textile reinforcement, woven fabric, and non-crimp fabric. And we developed, based on that results, the mold and the transfer concept, the resin application strategy and the process control, and we investigate the closing strategies and their influence on the critical process. And then basically compare the two variants, one direct form and the second one with a preform. And that's what you find here. Let's complete that picture before I talk about it. So the results of the process development and the comparison of the two process routes is what you see here. A complex component, as you can see, can be manufactured even better in the direct process. So we don't see any entrapments or any dry spots here. As the complex box corners are infiltrated at an early stage before they are being compressed. So when the permeability is higher, it's rather better to have them impregnated properly, then squeezed out, rather than to have a preform where the permeability is not given anymore, and we have too high fiber loadings in that areas that prevent from impregnation. So it was vividly demonstrated how a complex process could be systematically investigated, understood, and successfully transferred to manufacture complex demonstrator using this M to the power of 3 approach. The advantages of the mutual interactions of mechanisms could be demonstrated here and validated, also with some literature comparisons. To end that talk, or to finalize it, I want to quickly speak about some trends. Just a few short words about what we are facing right now in our daily work with composites is ecological and societal pressure. To a large extent, we have in Europe the European Green Deal. We have Biden that just a week ago stated that the US goal is to replace 90% of plastics with biomaterials, whatever that means in detail. It is a big announcement, and it emphasizes also us in the lightweighting and composite industry to look into the materials we are using. And I guess fibers based on natural resources is one thing, and a lot of research has been spent on that. But also on the resin side, there's still a long way to go, and there are materials to be preferred over others. And yes, this is just a glance. It's just 2 slides. Peep inside a complex topic when we look into the matrix system. What you can see here in the diagram is the global warming potential, which is caused by the production of 1 kilogram of resin. First, what you can see here is that especially the high-performance metric systems can cause quite a bit of global warming potential of up to 16 kilograms CO2 per kilogram. So one can also see that the values for the epoxy resins that's here are pretty much fluctuating. Reason for this is that the epoxy resin usually consists of different monomers and hardeners, and depending on the components being used, the global warming potential is changing. However, there are different kinds of actions which are under investigation to reduce the environmental impact. Using renewable energy sources leads to, of course, always to a reduction of the environmental footprint, but especially for the high-performance materials, the replacement of fossil-based to bio-based chemicals like aniline is under investigation. However, as in contrast to the carbon fibers, lots of components contribute to the global warming potential. The reduction potential has certain limitations. So we have to use recycled material and bio-based feedstock. And just to look into 2 material that we had a closer look to polypropylene and polyurethane, since they are quite established and often used, especially in the commodity field. It's heavily depending on the feedstock. So polypropylene you can derive with a natural source from wheat or sugarcane, and it's completely different in terms of their global warming potential. However, when we then, beside this, use recycled PP, we can significantly save up to 80% global warming potential, but we have to really utilize all the potentials in order to derive chemical building blocks from natural sources and return them into the loop, using them in a circular manner to get to that high savings. The fluctuation is somewhat higher for polyurethanes, because polyurethanes consist of two polymers components, polyols and isocyanates. For both are bio-based versions already commercially available. And also recycled polyols are under investigation. So depending on the combination of these components, the reduced potential can be up to 90%. In summary, what's the takeaway for these two systems? Wheat is best for polypropylene, sugarcane worse. So even these little things can make a lot of difference. And we have to use recycled materials and bio-based feedstock in the future. It's very interesting for polypropylene, polyurethane as mass polymers also being used in the composite industry. All right, I guess my time is over. Finalizing with just one slide, and I jump over the others, is basically a cluster that we founded, the Fraunhofer Cluster for Circular Plastics Economy, where 6 Fraunhofer institutes are commonly working in 3 divisions, materials, systems, and business, which are divided in 6 research departments in the field of how to get from a linear to a circular plastics economy by starting with a suitable product design. It's also the M-Power-to-3 approach in a certain way. There's a circular readiness level that you can find in the internet, where you can look at your products and get a first justification. We look into new materials, by self-reinforced materials. It's a new trend. We look into recycling technologies, chemical recycling and mechanical recycling, and how to win back building blocks that we can reuse. We use into monomaterial products, which are easily to dismantle and recycle. And what I wanted to point out is to develop this linear into a circular economy, you need a lot of players, and Fraunhofer has, what you can see here, a lot of partners working along that value chain to work on that, I would say, topic of the next 2 years, which are also very relevant for us in the field of lightweighting and composites. And therefore, there are a lot of new networks being founded, which I want to invite you to have a look at or to participate. All right, that's what brings me to the end of my talk. I want to thank all my colleagues who contributed to a large extent to what I was able and allowed to introduce to you today. It was a pleasure. Thank you for giving us the time. I want to thank all the industrial partners that enable us to be so close to a product and production system, all the governmental support that we got. And I guess we have a bright future with all the challenges, but engineers grow with challenge, sustainability, flexibility. How can we employ artificial intelligence in future? And how can we further grow with material innovation, which, by the way, are responsible for 2/3 of our overall inventions globally. Thank you for your attention. I hope there's a few minutes if there are questions to answer. Other than that, I'm happy to also answer questions via email if you are running out of time today. Thank you.
Thank you, Dr. Henning. I'm Jonathan Goodsall. I'll be fielding questions here or asking the questions. Please put those in the Q&A box. And yes, indeed, Dr. Henning, we will send these to you. So those, if your questions are not addressed here, we'll send these along, and Dr. Henning can respond to you. Let me summarize, first of all. There's a question, and I anticipate there might be some more questions along the lines of the sustainability. Rather than take any one of the specific questions, Dr. Henning, where would you point attendees to learn more of this context and the background you've presented about different energy inputs and so on, as you've walked us through a very big picture view of some of the impacts and the drivers on energy and sustainability. Where would you point this audience to for further learning or further reading?
Okay, I hope I got your question. Otherwise, please stop me. You mean in terms of sustainability question, right? Yeah. I guess what we definitely have to, and that's what I try to establish at the end, and I guess that would have been worth the whole presentation. We have learned a lot about this, how to use that material for sustainability. Now we have to rethink how can we make the material more sustainable that we use for contributing for sustainability, because we have a harsh, let's say, competition with the metals, which their intrinsic disadvantage is their density. So in order to still get to that savings over a product lifetime by employing composites as a wonderful material for the future, we have to look into the questions, how can we get to, I wouldn't say carbon neutrality, but closer to that. BMW was so successful with the implementation of these composites in their structures because they derived their fiber from Moses Lake in the United States, where they have been produced CO2 neutral with water energy. And that's a very important part of the puzzle, that they don't, let's say, take a backpack full of carbon footprint already with the fibers in the beginning, and then have a hard time to get to neutrality through the lifetime of a product with this business case of a vehicle. So I guess I want to guide the people to a more holistic product understanding, like engineers should have. We have to employ more life cycle assessment tools. We have to understand how we can incorporate the view from the beginning of circularity a little bit more into this evaluation. How can we value that? And where lightweighting and composites are really good is in saving energy during the lifetime. So we have to take that out so that we don't get a deteriorated picture. And then we see exactly what energy do we need, where do we derive our materials, can they be replaced with bio-based materials or with chemical building blocks based on natural materials, and how can we close that gap between CO2 certificates we get back from incineration or recycling or whatever we get this gap as much close. So we have to, when we start developing our products and materials, we have to think how can we bring them back in the circle as much as possible. And if it's not feasible, which is a totally valid approach in my opinion, how can we use the energy out of that material after the life cycle, which is valid too, because it's a high energy material which can be utilized.
Thank you. We've got time for one more question, and it's a question about the new classes of polymers. Have you investigated new classes of polymers like vitrimers or malleable thermosets that can be more easily recycled?
Yeah, unfortunately, we are working on that, but that's not my field of expertise. We are working on a bio-based system. But I'm the wrong person to answer that question in detail. We are working with these materials, but they are coming from a different institute, the Institute for Polymer Chemistry in Potsdam, Berlin. They do a lot of that work, and but that's more the input for us, since we are not in the synthesis side of things, of polymers.
Very good. Well, thank you. Thank you again, Dr. Henning, for your presentation. Thank you to the audience for your participation. And a reminder that this presentation will be posted on cdmhub.org, and we will send the questions to Dr. Henning for him to answer. And we'll look forward to seeing you all again here May 18th. We'll hear from Dr. Remo Ackerman and about composites forming simulations. So thank you all again, Dr. Henning, thank you for your presentation.
Thank you very much for the opportunity. Happy Easter.
Thank you all.